After this class, I will post scores and the key for exam 1. I decided to weight each question at 15 points. So if you multiply 24 times 15, you will see that yields an earnable score, maximum possible earnable score, which is considerably greater than the base value for the exam that's stated on the syllabus, which, as I've already told you, is the way I play the game. Lynn Pham is changing her office time. I simply fail to realize when I drew up the syllabus for this gathering that many of you, I'm sure, will be coming after help on Thursdays and Fridays of exam weeks. For obvious reasons, since the exams are all Friday evenings. So, with her moving office time to Friday, this will make more out-of-class assistance available for you folks. Exam weeks. So we proceed. What we're now looking at are various special topic considerations for water solutions of acids, Bronsted-Lowry acids and bases, and the equilibria which are involved. Oh, one more announcement. For your special entertainment, Special Quiz 1 is now available. I posted it yesterday. Download from Sakai and have at it. I forget the due date, but it's at least a week. I think it's a week, something like that, a week from today. And what we do today, if not today, tomorrow, should provide you with all the foundation that you will need to be able to wrestle successfully with Special Quiz 1. That's why I was in no hurry to develop it, because special quizzes always tackle difficult stuff. And you, as yet, were not prepared to tackle this particular difficult stuff consideration. But with today's conversation, tomorrow you will be. So, the first major special topic we looked at regarding Bronsted-Lowry acid-base chemistry was that of buffers. Included with that was indicators. Now we proceed to look at some more of these considerations. What is the hydronium ion molarity, pH if you wish, for very dilute solutions of Bronsted-Lowry acids and bases? What you, in this case, must recognize is that oftentimes for such solutions, you have also to pay attention to the ionization of water itself, which means Kw. For example, I trust by now you've taken a look at the illustration in the notes of calculating the pH for 3 times 10 to the minus 8 molar HCl solution. That's the label you see on the bottle in the lab. Well, you will realize, of course, that the HCl is ionized 100%. That provides to the solution a hydronium ion molarity contribution of 3 times 10 to the minus 8 molar. But if you stop there and say for this solution, which has got to be acidic because it's got a strong acid solute, that hydronium ion molarity for this solution is 3 times 10 to the minus 8 molar, and report a pH that's above 7, you have to recoil in horror. You say, what's going on here? This is an acid solution. It cannot be basic. It cannot have a hydronium ion molarity that's less than 1 times 10 to minus 7. It cannot have a pH that's greater than 1 times, that's greater than 7.0. It's impossible. So again, what you must always think about is chemistry, and let the arithmetic that's necessary follow thereafter. But if instead you try to solve problems in real chemistry by looking for a recipe in which you can shove data and push buttons, you lose. You can't succeed like that. Always chemistry, first and foremost. So as soon as we recognize that this has got to be an acidic solution, we immediately recognize that there's got to be a source of hydronium ion in the solution beside the solute. Has to be. Well, the only thing in there that's beside the solute is the solvent, so that must be the solvent. Next question. Do you think in this solution the solvent will provide a hydronium ion molarity of 1 times 10 to minus 7? You think in any water solution, autoionization of water always generates a hydronium ion molarity of 1 times 10 to minus 7, and a hydroxide ion molarity of 1 times 10 to minus 7. Do you think that's true? Do you think that's true? I sure as hell hope you don't think that's true. Because if I have a solution which is distinctly basic, it cannot possibly have a hydronium ion molarity which is anywhere near 1 times 10 to minus 7. So what impact does the acid solute or the base solute exert on the autoionization reaction of water? Does it cause that reaction to go in the forward direction or the reverse direction? Which way? Which way? I'm listening. This is the chemistry. In this HCl solution, will I cause the autoionization reaction of water to proceed to further extent? Or will I cause it to go in the opposite direction? Which way? Reverse. Reverse, you're damn right. It's just like, you remember the solution that we talked about where we had HCl solution dissolved in deionized water and got the hydronium ion molarity? Don't worry, it never storms in Florida. Okay. Then we follow that up with the acetic acid solution, treated with the same amount of HCl, and ask the question, in the HCl treated acetic acid solution, will the acetic acid still ionize to contribute measurably to the hydronium ion molarity of the resulting solution? We found out no, because the hydronium ion supplied by solute HCl stopped the ionization of acetic acid. So it shoved the reaction, hydronium ion acetate ion, back toward acetic acid. All right, so let's look at question 1844. 5 times 10 to minus 8 molar sodium hydroxide solution. So immediately we can say for this solution that the hydroxide ion molarity for this solution minimum has got to be 1 times 10 to minus 7. You accept that statement? Now notice, this statement is not saying that 1 times 10 to minus 7 moles per liter hydroxide ion has come from this. That statement doesn't say that. That statement says we have a water solution which we know is basic because we got a basic solute in there. And therefore the hydroxide ion molarity cannot be smaller than 1 times 10 to minus 7. Okay? Now, is the hydroxide ion molarity for this solution 1 times 10 to minus 7? That's a possible, but let's take a look and find out if that is the correct hydroxide ion molarity. Well, we reminded ourselves that for such a case, we've got to look at Kw. So here's Kw. Let's let the hydronium ion molarity be represented by X. Because in this solution, there's one and only one source of hydronium ion. What is it? Water. But there's two sources of hydroxide ion, isn't it? The solute, which provides 5 times 10 to the minus 8 moles per liter of hydroxide ion, plus solvent water. And if solvent water, by this reaction, produces a hydronium ion molarity of X moles per liter, then what will be the equilibrium molarity of hydroxide ion? How many sources? 2. Here's what we got from the solute. How much are we getting from this reaction? We're getting X, aren't we? So we got 2 sources. This from the solute and this from the solvent. So how do I represent the hydroxide ion molarity for this solution? You got it. And now we've done the chemistry. The rest is simple arithmetic, algebra, whatever you want to call it. So here we go. So given that X represents the hydronium ion molarity at equilibrium for this solution, and given that this solution is very dilute, I want you to give me a speculative value for X, the hydronium ion molarity. I do not want you to take that thing, multiply it out, recognize that algebraically it's a quadratic, and apply the quadratic recipe. Because I will flog you if you do that. Because you've just told me you don't want to learn chemistry, and I won't have that in here. But I suspect strongly you all know that by now. I want a reasonable speculation for the hydronium ion molarity for this solution. I heard a vote for 1 times 10 to the minus 8. Now what do we know about the hydronium ion molarity before we actually calculate X? That's where the foundation for making your speculation on a reasonable basis comes from. What do we know about the hydronium ion molarity? Is it going to be close to 1 times 10 to the minus 7? Is this solution not very dilute? So it's going to be close to 1 times 10 to the minus 7. Now, if the solution is extremely dilute, it can be 1 times 10 to the minus 7, but it cannot be greater than 1 times 10 to the minus 7, because it's a basic solution. Now, of course, in this basic solution, if we find that X is 1 times 10 to the minus 7, then we will have proved that the hydroxide ion molarity is also 1 times 10 to the minus 7. Couldn't be anything else. So, without as yet doing any arithmetic, but by recognizing this as an exceptionally basic solution, we expect the hydronium ion molarity for very, very dilute conditions to be 1 times 10 to the minus 7, or something that's smaller than 1 times 10 to the minus 7, but not a whole lot smaller than 1 times 10 to the minus 7. So after having said that, now I want speculations again to be made. I heard a speculation for 1 times 10 to the minus 8. That's 10 times smaller. That's considerably smaller. 8 times 10 to the minus 8. 5 times 10 to the minus 8. All right, just for fun, let's try the 5 times 10 to the minus 8. That would make this 5 times 10 to the minus 8, and would make this what? 5 times 10 to the minus 8 plus 5 times 10 to the minus 8. Really tough. I mean tough. Figure out your log table and your IBM mainframe and all that stuff. Like hell. That's 1 times 10 to the minus 7. So I ask, 5 times 10 to the minus 8 times 1 times 10 to the minus 7. What's the result? I'm listening. I don't want to see any push buttons. 5 times 10 to the minus 8 times 1 times 10 to the minus 7. What is the result? 5 times 10 to the minus 15. And that's a good deal smaller than KW, isn't it? So with this simple test, we have proved that the true value for x compares how to 5 times 10 to the minus 8. It's got to be bigger, because we got a value that's too small for this combination of terms, considerably smaller than kW. So, we haven't done anything fancy, and certainly nothing hard from an arithmetic standpoint. And we got x in a box, don't we? It's only one significant figure for this concentration. So x is 6 times 10 to the minus 8, or 7 times 10 to the minus 8, or 8 times 10 to the minus 8, or 9 times 10 to the minus 8, or 1 times 10 to the minus 7. Period. It's got to be one of those. Right? We haven't done anything fancy. We've already got x in this little box. Now, if you looked at this, or pardon me, or thought about it before we had this conversation, you have realized that 8 times 10 to the minus 8 does the job. Let's verify that. This is 8 times 10 to the minus 8. 8 plus 5. 13 times 10 to the minus 8. Now comes the real hard part. What's 8 times 13? 104. Now let's put in the decimal point. Pardon me, 104 times 10 to the minus 16, right? Because I had 5 times 10 to the minus 8 times 13 times 10 to the minus 8. So I got 104 times 10 to the minus 16. Now let's change the exponent to 10 to the minus 14. That makes the value become 1.04. You agree that's kW? Done. All done. And we haven't done anything fancy nor difficult. And I hope, once again, we've demonstrated that if you think about the chemistry of the problem, tackling it is immediately tenable. But if you start fooling around with quadratics and stuff like that, you are wasting your time. And you are failing to learn chemistry with that kind of approach. And that's what most textbooks do. One more reason why I don't let them damn rotten things in this classroom. They stand in the way of learning chemistry, and I won't have it. You only see that junk in general chemistry books. It's sad. You see good analytical books, organic books, PChem books, you don't see any of that stupidity. But general chemistry text is rife with that garbage. And it's sad, really sad. Because general chemistry is the most important chemistry, period. Provides foundation for all other chemistry you're going to do. Plus, it is the chemistry that is presented to the largest, most impressionable audience by far. We have more students in Chemistry 2045 in the fall than we have if we sum up all the chemistry students in Chem 2, organic, analytical, PChem, graduate courses, you name it. There's more in Chem 1. And by golly, they ought to have a good first impression made on them. That's why I want to teach the course. How about that? All right, on we go. 1845. I choose to tackle 1845 because, as with every group of students I have seen at this stage of the game, many of you have succeeded in convincing me that you have severe disrespect for significant figures. As I have said before, and as I will say again, I'm sure many times, if every time you make a sig figure, you have to pay me $1, wow, would I be rich at the end of a term. Better yet, though, I take the money and for everybody who passes, we'll have a nice pizza and beer party. Paid for by all the Sig Fig violators. For example, 1 times 10 to the minus 8 molar HCl, 1.0 times 10 to the minus 8 molar HCl. Can these solutions have the same pH? Now, without doing any arithmetic, you can immediately respond to that question. Could these solutions have the same pH? Yes. Absolutely not. How could they have the same pH? The first datum is 1 Sig Fig, isn't it? The second datum is how many Sig Figs? 2. Which means for the first pH you're going to have 1 Sig Fig, and the second pH you got 2 Sig Figs. There you go again, violating Sig Figs. I told you. Disrespect for Sig Figs. When you're in analytical class, you better have great respect for Sig Figs, because they charge heavily in analytical class for Sig Fig goofs. Right? How about that? Put another way, for neutral water, I've just told you that a pH of 7.0 and a pH of 7.00 are not equal pHs. How about that? Now then, this is what, now we're getting at the intent of 1845. Because I've had students who will operate on 1 times 10 to the minus 8 and go through the KW arithmetic, which we just showed you, and find out that the correct value for X for this solute molarity, HCl solute molarity, X 1 times 10 to the minus 7, pH 7.0. So what does the non-thinking student do when he jumps to this solution? He writes down X is 1.0 times 10 to the minus 7 and the pH is 7.00 and flunks, because Sig Figs have again been trashed. You now know how to do the arithmetic, because for the 2 Sig Fig solute molarity, X is 1.1 times 10 to the minus 7, for which the pH is 6.96. You know what to do, work through the arithmetic. And we go to 1839. Now, we've been talking here about solutions which are quite dilute. And for the cases considered here, KW had to be considered. Had to be part of the puzzle. Well, tell me, before I go to that, let's say I'm in the lab and I hand you a bottle which bears this label. Whoa-wee, is that dilute? For that solution, what's the hydronium ion molarity? Right there. All right, if you don't like that, what's hydroxide ion molarity? I'm listening. I don't want to see any push buttons. I don't want to see any calculation going on. Yes! There's hydronium ion molarity and the hydroxide ion molarity, because that baby is so damn dilute that the impact of solute on pH is nothing. You recall a question like that on exam 1? Huh? There was one there. It was a 10 to minus 10 molar solution. It's appealing to you to think And there's no way you get through this without thinking. It has to be done. That's where the understanding comes from. No recipe following. Forget that nonsense. All right. Let's go to a greater extent, a dilution extent. How about infinite dilution? I'll give you a simple-minded example of infinite dilution. We'll go to the Gator swimming pool over here, Olympic-sized swimming pool. Any of you go swimming over there? Good thing to do. We're going to fill that swimming pool with deionized water. And in it, we're going to put in one acetic acid molecule. You think that resembles infinite dilution? Yeah, I think so. Okay. The $64 question is, Ka for acetic acid is 1.8 times 10 to minus 5. In this swimming pool, one acetic acid molecule, from an equilibrium analysis standpoint, will the acetic acid molecule remain as such, or will it become hydronium ion by proton loss, and in so doing, the acetic acid molecule originally added to the system has converted to acetate ion? What will happen? The acetic acid molecule stays as it is, or it becomes hydronium ion acetate ion? Here's a minor, I don't know what that is. All right. Let's go back to the swimming pool. Fish out the acetic acid molecule. And this time add one acetate ion. Will the acetate ion stay as such? Or will the acetate ion react with water and produce hydroxide ion and the acetic acid molecule? Because acetate ion is a Bronsted base that's stronger than water. What will happen from an equilibrium analysis standpoint? I hope you recognize that for the acetic acid solution I just described, if you have concluded that the acetic acid molecule reacts and becomes hydronium ion acetate ion, and then for the second system I described, you've concluded that the acetate ion reacts with water and becomes an acetic acid molecule as hydroxide ion is produced, that both of these statements cannot be correct. That's impossible. Because for the first case, if the acetic acid molecule in fact reacts with water and converts to a hydronium ion and this acetate ion, you will have duplicated the second solution. Right? Because in the second solution, we put in one acetate ion, that's all. Do you think for the acetic acid solution, making this one additional hydronium ion has any impact at all on the concentration of hydronium ion in my swimming pool? I hope you think no, because it can't. There's a number of hydronium ions in that swimming pool. At a molarity of two significant figures of 1.0 times 10 to minus 7 is enormously huge compared to the one hydronium ion I made by the acetic acid molecule ionizing on reaction with water. So here we go with page 1839. What happens at infinite dilution for various and sundry weak acids and weak bases? First, this statement. At infinite dilution, the hydronium ion and hydroxide ion molarities must be equal, and they must be equal to 1.00 times 10 to minus 7 molar. You agree with that? At infinite dilution. I don't care what the solute is. Independent of solute. At infinite dilution, I must have hydronium ion and hydroxide ion molarities equal. Is that fair? Why is that fair? Tell me, at infinite dilution, in essence, what kind of a system do I have? Pure water, right? How about that? Now then, statement. If Ka is a number that's bigger than 1 times 10 to the minus 7, the acid ionizes to an extent in excess of 50% at infinite dilution. But if Ka is a number less than 1 times 10 to the minus 7, at infinite dilution, the acid will ionize less than 50%. And of course, the ionization we're talking about is the acid reacting with water. Okay? So I asked the question, if Ka for the acid is 1 times 10 to the minus 7, to what extent does the acid ionize at infinite dilution? 50%. Oop. So, before we proceed with any arithmetic, you're now realizing that you have to tack on some additional considerations to the QPSI stuff, or PSI stuff with which you have so far been programmed. Well, QPSI, okay? Because now you're realizing, if I have an exceptionally dilute solution of acetic acid, which has a Ka value of 1.8 times 10 to the minus 5, which is 180 times bigger than 1.0 times 10 to the minus 7, that if the solution of acetic acid is particularly dilute, then the principal solute species in the solution may well be what?
Water.
Solute species in the solution. Hydronium ion and acetate ion, you betcha. Now the principal solution component will of course be solvent. But if I ask for principal solute species, because you always got to answer the question that they asked. I got a kick out of it when students are in my office wrestling with problems from my past exams and quizzes and saying, what do they want? I'm they. I wrote all that stuff. My quizzes, my exams are all original products. All original. I invent that stuff because I love doing it. And it keeps me on top of this stuff, because this stuff is tough. This stuff is important, though. That's why I make this painstaking effort to go through this stuff with you folks, because I know it's tough. You're not going to get this stuff out of any textbook, period. That's it. Okay? So we'll take a look at acetic acid and acetate ion, which we just talked about. Ka, Kb. And we really, based on our conversation, you already know the answer. In the extremely dilute acetic acid solution, I will not find acetic acid molecules. At least not in abundance relative to hydronium ions produced by the ionization of acetic acid and acetate ions. The molarity of hydronium ion and acetate ion produced by the ionization of acetic acid have got to be greater than the acetic acid concentration itself in a very, very dilute solution. Not so for the acetate ion solution, because Kb acetate ion is a good deal smaller than 1 times 10 to the minus 7. So I don't care how dilute you make sodium acetate solution. You cannot get it to react with water to an extent which even comes close to 50%. So I'll use Ka for acetic acid. Here it is. And we've already recognized at infinite dilution, there's the hydronium ion molarity of 2 sig figs. So at infinite dilution, the acetate ion molarity to the acetic acid molarity is this. 180 to 1. The molarity of acetate ion is 180 times greater than the molarity of acetic acid. And if I start with acetate ion, I get the same result. I have to. Here it is. So with this simple arithmetic I've demonstrated that acetic acid, under extremely dilute conditions, will convert practically entirely to acetate ion. Don't you think a molarity of acetate ion that's 180 times bigger than the molarity of acetic acid itself? pretty much is saying the acetic acid is gone 100%, practically speaking. And one more comment. At 50%, or pardon me, 50% ionization of acetic acid or acetate ion, which would give this molarity at infinite dilution, is impossible. Impossible. We just showed that this is impossible. And so we now go to polyprotic Bronsted-Lowry acid-base systems. Oh, one more question on this stuff. Take a look, if you will, at question 1847 and 1846. This is page 1840 in the Chem Notes. 1846 is one of the rare occasions where I'm asking you to do a plug and chug. The formula, which is derived and printed on page 1839, about 2/3 of the way down the page, which says max percent ionization at infinite dilution. Page 1839. Ka times 100% over Ka plus 1 times 10 to the minus 7. You see that? It's on the information sheet. So if you're dealing with a water solution of an acid, all you got to do is look up a Ka value from our info sheet. For a base, it's Kb times 100% over Kb plus 1 times 10 to the minus 7. So then you have to calculate Kb for the base, but you know how to do that. So for HOCl, you get out the info sheet, look up its Ka value, apply the recipe. And you get 22% max percent ionization, because KaHOCl is a number smaller than 1 times 10 to the minus 7. And the next question, see it? How is it possible to get a weak Bl acid with Ka less than 1 times 10 to the minus 7 to react to an extent which exceeds 50%? Now look at the question as it is stated. We said to get it to react to an extent which exceeds 50%. Did we say to get it to react by dilution with water? We didn't say that, did we? How about this acid? We've already done a fair number of calculations with this acid. The acid-base table tells you the Ka value, 5.6 times 10 to the minus 10, which is a good deal smaller than 1 times 10 to the minus 7. And I get ammonium ion in a water solution to react to an extent which exceeds 50%. And I get ammonium ion in a water solution to react to an extent which exceeds 50%. Yes or no? The answer is of course, but not by reaction with water. I got to partner up ammonium ion with a better H plus grabber than water. How about hydroxide ion? Does ammonium ion react with hydroxide ion to a large extent? You're damn right. And so, proceed with the polyprotics. First remark, there are 3 categories of polyprotic types. Let's write them down. call them 1, 2, 3 or A, B, C. I don't remember. Let's call them 1, 2, 3. Category, small Roman 1, parent acid is strong and molecular. Category, small Roman 2, parent acid is weak and molecular. Category 3, parent acid is specifically a hydrated metal ion. Each of which is weak. At least all that are known are weak. Okay? Now then, there's a missed formula on page 1841. You see the sulfuric acid molecule formula at the top of the page? I flunked. Fix that formula. You see what I'm talking about? The sulfuric acid molecule formula at the top of page 1841, printed in bold, is dead wrong. Well, I'm now taking the necessary steps to put a stop to that kind of stuff. Because I will no longer ever send work to my publisher or any publisher for them to type. Never. Because they don't know chemistry. So after they type all the stuff which I send them, in order for this stuff to be correct, I have to reproof all this stuff all over again, and I'm not doing that anymore. Now I will generate all camera-ready pages to be photographed and turned into lab manuals and textbooks. And I won't have to worry any longer about poor, struggling people working in a publisher's office trying to generate all this chemistry of which they understand none because they never were chemistry students. No, I'm not doing that anymore. I have now developed sufficiently good word processing skills so that I can handle it. And on I proceed. Now then, statement of these three subcategories of polyprotic bronzoluric acid, same applies to bases. Parent acid, strong and molecular, is going to require equilibrium analysis, not for the parent acid itself, because if the parent acid is strong and molecular, to what extent will it react with water? 100%. But if it's polyprotic, like the most common strong molecular polyprotic acid, which is known sulfuric acid, which is diprotic, okay? In making the sulfuric acid solution, of course, all sulfuric acid molecules added ionize by reaction with water 100%. But then what's the fate of hydrogen sulfate ion? That's where the equilibrium analysis comes in. For case number 2, there's a number of examples in the acid-base table. Hydrated CO2, H2S, oxalic acid, a whole bunch of examples. Phosphoric acid in the acid-base table. we will find that calculating pH, hydronium ion molarity for case number 2 is the simplest. Because we pay attention only, we will need to pay attention only to the first Ka value for the acid. And prove that the second Ka value won't mean anything, too small. And then when we get to case number 3, the hydrated metal ion, we will have great fun. And at that time, we will introduce you to the final consideration to which you must be introduced so you can take any water solution apart in detail so as to be able to calculate correctly the molarity of each and every species in the system, no matter how small that molarity might be, if their existence depends on pH. That will require that at that time we talk to you in a formal fashion about charge balance. It's not hard, but it's something we haven't done yet. And that's what you're going to need to tackle special quiz number 1. All right, here we go. There's an example for a sulfuric acid solution that's in the notes. I'll take a parallel example where I'm dealing again with a sulfuric acid solution, but the initial molarity is different. This will be thousandth molar. So here's the formula which corresponds with sulfuric acid structure. That's why I use it. And here's the good old textbook formula, which in 2045, if you're given the textbook formula as a 2045 student and you're dealing with Lewis structures, and I ask you to write the Lewis structure for the sulfuric acid molecule, my bet is you'll get it wrong. Because you write a Lewis structure when you have the hydrogen atoms covalently connected to sulfur, because that's the implication of that horrid formula. One of my 2045 colleagues didn't believe me. He kept on saying they know this. I said, how the hell can they know it? They're just studying chemistry. How can you say they know it? So he tried it. He tried it with nitric acid, HNO3. And each and every student drew a Lewis structure where hydrogen was covalently connected to nitrogen. Therefore, each and every student was dead wrong. And he said, you were right. Wonderful. No, will you teach it the right damn way? Never mind me being right. That's immaterial and irrelevant. This is for students to learn. Okay. A. Pure sulfuric acid at NLC by itself is a liquid. It's a nasty liquid. If you get pure sulfuric acid on your person, because we have, well, it's not entirely pure, it's about a 98% solution, you know, the concentrated sulfuric acid that you use in laboratory exclusively for the nitrate ion test. Okay? I don't want you using that for anything else because of its danger. If you get some of that on your person, it is extremely and exceptionally quick, fast, damaging. And not because it's a strong acid, but because it is a potent dehydrating agent. And you will see your skin dehydrated right before your very eyes, turning into a carbonaceous lump of burnt tissue. A simple demonstration of this is to take some sugar, for example. Are you aware the structure of sugar has a bunch of OH groups in it? Okay. You think that OH groups can get together with each other and convert to water? So if I take a sugar molecule with a bunch of these OH groups and treat it with concentrated sulfuric acid, which is this potent dehydrating agent, it causes a whole bunch of these OH groups to react with each other, convert to water, which is removed chemically by the sulfuric acid. So what does the sugar convert to? A carbon lump. And go curl up in the air, look like this, looks like a carbon snake. It's dangerous. Maybe someday I'll do it for fun. You can see this on Google. You can Google sugar treated with sulfuric acid. Because this is something that a lot of chemistry teachers, they get their jollies from this. Hey, but demonstrations, as far as I'm concerned, have to be used strictly and exclusively to serve the purpose of learning, not for entertainment only. Back to this. What the hell is this piece of paper here for? I don't know. Oh. Now, what do you know about the extent of this ionization reaction? 100%. So if I see this label on a bottle, right here, like a reagent bottle in the laboratory, I know immediately that the hydronium ion molarity in this solution is at least what value? What? Thousandth molar. It's got to be at least, because this went 100%. So if this is initially a thousandth molar and this goes 100%, then initially this has got to be a thousandth molar. And initially this has got to be a thousandth molar. Nothing fancy about that. But here's where the calculation part comes in for sulfuric acid solution. And what's the extent of this reaction? Well, first we recognize that categorically this is a weak Bronsted acid. If you look at the acid-base table, you see Ka for this is 1.2 times 10 to the minus 2. Now that's a pretty big number as far as Kas for weak acids are concerned. And based on the conversation we just had a moment ago, given that 1.2 times 10 to the minus 2 is a number which is a hell of a lot bigger than 1.0 times 10 to the minus 7, would you accept my statement that from this we may legitimately conclude that you don't have to dilute hydrogen sulfate ion very much to get it to ionize by reaction with water to significant extents? That sound fair? K value for hydrogen sulfate ion, a weak acid, but its value 1.2 times 10 to the minus 2 is a whole lot bigger than 1.0 times 10 to the minus 7. A whole lot bigger. 1.2 times 10 to the 5th bigger. 120,000 times bigger. So you don't have to have hydrogen sulfate ion under extremely dilute conditions to get it to react with water to very large extents. But since it is a weak acid, we'll put its ionization extent as 0 to 100%. And what will this extent depend on? We did this last week. What does ionization extent depend on for a weak acid? Depends on two things. What? I'm listening. Ka and concentration. Is the ionization extent directly proportional to concentration or inversely proportional to concentration? Inversely, right? The more dilute the solution, the greater is the ionization extent. All right. Now then, based on what we have so far said, we can now recognize all that we need to recognize regarding sulfuric acid solution to calculate each and every property of a sulfuric acid solution in which we might be interested, like hydronium ion molarity or equilibrium molarity of each and every component of this system. Because from this first reaction, we recognize that the hydronium ion molarity is at least M sub I. Right? The label on the bottom. Thus, H3O plus. At least M sub I. Or hydronium ion concentration minimum is M sub I. Same thing. But from the second reaction, we can now say matter-of-factly that the hydronium ion molarity for any sulfuric acid solution is equal to M sub I plus what? Well, let's play a game. I'm going to put a 100 over the formula for my initial solute sulfuric acid. Now, what do we recognize about these initial 100 sulfuric acid molecules? After this first reaction, are there any of these left? No, they're all gone. So after the first reaction, but before the second reaction, I got 100 of these and 100 of these. All right? So when the second reaction begins, I'm starting with 100 of these. But some of these are going to go away. And when some of these go away, from a material balance standpoint, to what do these things convert? I'm asking for material balance for sulfuric acid solution for sulfur-containing components. To what do these convert? Is hydronium ion got sulfur in it? No. Sulfate ion, right? Okay. So if I ask you now to write a material balance equation for sulfuric acid, for specifically this solution, MB, material balance, you'd write 0.0010 equals, this is material balance for sulfur-containing stuff. What are you going to write over here? You going to write the formula for this? Are there any of these in the solution after you prepare the solution? Not a damn one, so you don't put that in there. Done. The sum total molarity for this system of hydrogen sulfate ion and sulfate ion has got to equal 0.0010. So we go back to this. We're playing our game. Started with 100, they all went away. 100 of these were made. 100 of these were made. So when our second reaction begins, I'm starting with 100 of these. Now, pick me an ionization extent for the second reaction. 80%. Okay, I'll take 80%. Goes 80%. We'll write down imagine. B goes 80%. Now watch out, this is really tough. 80% of 100. I'm listening. 80! How about that? Goody. So, but the second reaction goes 80%. By the second reaction, I've made 80 of these and 80 of these. You ready? Okay. And how many of these will be left? I know 80 from 100 is pretty tough. 20. How about that? Okay. Now comes the $64 question. In total, how many of these do I have? I got from the first reaction 100, and I just made 80 more, didn't I? And so, the hydronium ion molarity in a sulfuric acid solution is M sub I, the label on the bottle, which is telling me how much I got from the first reaction, plus the sulfate ion molarity, right? Because the sulfate ion made by the second reaction is equal to the contribution to the total hydronium ion by the second reaction. And that's it. With this, you can now crack any sulfuric acid solution in terms of concentration calculation for any of these system components, period. So, we shall proceed. We said we're looking at 1,000th molar. And we reminded ourselves that the equilibrium computation that you will have to do involves the second reaction, because that's the one that's governed by equilibrium. Not the first. No equilibrium there. That one-way street. So here's what we got so far. Now I have one remaining question regarding the general composition of any sulfuric acid solution, the answer to which follows from what we've already done. For each and every sulfuric acid solution, how does M sub I, the label on the bottle, compare to or relate to hydrogen sulfate ion molarity and sulfate ion molarity? How does sulfate ion molarity and hydrogen sulfate ion molarity for any sulfuric acid solution, how does that relate to M sub I? Remember what we did here would be? We imagined to start with 100 of these, and we took the speculation of 80% ionization extent. So out of the initial 100 of these, 80 of them went away and became sulfate ion, and 20 of them stayed behind. But if I add 20 to 80, I get 100. So that tells me this. Right? How about that? So if you wish, where I wrote hydronium ion as M sub I plus sulfate, I can write it as this. You like that instead? If M sub I is this concentration sum, if I put that in for M sub I, don't I get this? Hey. Now, I know for a fact that many students at this stage of the game are mortified by this. They don't realize from an algebra standpoint that this is nothing. This is simple algebra, as simple could be. But they see these formulas. So they go, ah, because of the chemistry. If I write down X and Y, they're all happy. X and Y is fine. But if I write this formula, they go, ah, ah, look at that horrible formula. I don't want you writing X and Y, damn it. Because if it puts you in the habit of forgetting the chemistry of the system. There's no need to do that X and Y stuff. But if you wish, when I'm not looking, I can't stop you. But I guarantee, when I ask you about stuff like this on Quiz 2, which will be this week, or Exam 2, or coming exams, I will hover above all of you as an ethereal spirit. And in my hand, I will have a huge thwacker device. And if I see you write down X and Y for this, whap, whap! Don't do that! If I see quadratic for this, whap, 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 whap! You got that? We'll pick it up from this point tomorrow.